Let me just give you one concept. So, how did the first order differ from zeroth order? They were for all and there exists. And generalized modus ponens, what did we do? We will make in some substitution such that after substitution, whatever we have as the premises are known to be true in the knowledge base, or they are equivalent of something which is a knowledge base. So what we'll do is answer a very funny question that if I'm given in two pieces of knowledge, propositionalize in terms of variables with constants, of course, you could actually say if they are exactly the same character by character, they are same. Now the problem is that my propositions have variables. Variable could take in any value. So I have to answer the question if two terms are exactly the same, or by some substitution, by some technique, by replacing variable with something, they can take in the same value. And the concept is called as unification. So let's directly come on to the example. I have studies AI, comma, best friend of R1, and this exists in my knowledge base, and I have a premise, or anywhere in the functioning I have studies X best friend of Y. Now these two are exactly equal if I apply the substitution X is equal to AI and Y is equal to R1. They both become exactly equal. I could make it a little bit more interesting. I could say what if it's Y over here and what if it is R10 over here. Still they're equal. And I say X is equal to AI and Y is equal to R10. Still they are absolutely equal. Let's make it more interesting. So I say R6. Now are they equal? And the answer surprisingly is yes, still both of them are equal with the substitution X as AI and Y as I do not know, but best any substitution such that best friend of Y is equal to R6. So they would still become equivalent. So Y could be such that the best friend of Y is equal to R6, and that's what makes them absolutely equal. I could make it even more interesting by saying best friend of Z. So X is of course AI. Now you could have many options. Y is equal to R1 and Z is equal to R1. X is AI, Y is R10, Z is R10. Because it just says best friend of Y is equal to best friend of Z. That will be true for any Y and Z. Of course, it will be true for any Y and Z. And here is where I place a constraint in unification that I'll have the most generic or most general unifier. This substitution list is called as unifier because after that substitution, two things unify to become one. They become exactly the same. So it's called as a unifier. So in this case, I will, instead of all these, I will just take X is equal to AI and Y and Z as equal. I do not commit to a value, it's most general. I say as long as the value are the same, it absolutely doesn't matter. the most general unifier. Let's say things which will fail because I haven't taken the failed example. So studies AI comma X and studies robotics comma Y, it fails. Unify. AI can never be equal to robotics. And of course, I haven't been mentioning the variables, but I've been telling you what the variables are. Most of the times, I'll just tell you what the variables are. So, X, Y, Z were the variables. So, it absolutely fails. Surprisingly, this also fails. There's no way the friends relation can become equal to studies. Unify studies AI comma X, and let's bound it to a value. So let's see what happens when I do this. X is equal to AI and X is equal to R10. X cannot have two values, it fails. However, surprisingly, if I just do a renaming, variables you can rename, there's absolutely no problem. Does not fail. So X is AI and X2 is R10. That's absolutely okay. Okay, so we have something called as unification that tells me if two things under some substitution can be made equal or not. And the wonderful thing is, it could be used for whatever we learned in the zeroth order logic to make the premise of the rules true, to check if we have the goal satisfied by some substitution, and therefore I could just uplift anything from zeroth order logic to the first order logic as long as I have my unification done, which means two things are really equivalent under some substitution. So as long as the variables are gone, I am extremely happy about it. One thing in unification you might have to consider is the fact that if I want to unify X with best friend X, it might appear okay, X is a best friend, but then of what? X, but that's practically not possible. I'm friends with myself. That's called as a occur check. So all that you say is that you check if the variable that you have is also occurring in the relation, and then it will probably be a idea to say that x is equal to best friend of x is absolutely not possible. Now, because we are doing in unification, and that's the only important thing that you'll study in first order logic. So let's just very quickly see as another example how do we go upon actually unifying two things and then to write down a small pseudocode. So say I want to unify studies AI comma best friend of X with studies AI comma Y. or let me make it complicated, best friend of Z, and the go C over here. So I'll completely pass this thing up, and how I'll pass this thing up, so it studies, so this entire relation could as well be studied in the form of the name of the function followed by the list of all the arguments. Now just a list of arguments, so the first argument is AI and thereafter everything else. The second argument is what is the best friend of X, so I have the best friend as the name of the function. Okay, it's a name, I mean, it's everything else, it's a function, so let me go one level up, so that's best friend. And the argument list, that is what is a X, and similarly here, studies, and all the arguments around here. So the argument is just a list, so the first and everything else is nothing but best friend. Oops, they became exactly equal. Bad example. Anyhow, so I go upon saying that studies exactly match. AI can match with C by C as AI. Wonderful. Best friend match and X and Z. So I can have X and Z, and that's exactly what my algorithm will be doing. And no surprise that you go in a typical depth first search manner. So I say unify. The first let it be X, the second let it be Y, and theta is all the substitution made. So from the root to the branches and everything, I'll do some substitutions, and as soon as I do some substitution, I'll maintain it in a variable which is shared by reference. So looking at the above example, so X and Y both could be just a constant, R1, R2, R3, I'm not sure if I had that, AI just a constant, or they could instead just be a variable, x1, x2, x3, or they could actually be a list or a function or a relation. So let's say that if it's a function or a relation, we say a function or relation is nothing but something which is more compound. Okay, and theta is of course the substitution done so far. So with this, I try to really see what can I do about this, and all that I'll be doing is that I will be going it in a depth first manner. So let's handle all these things one by one. The easiest thing that could happen if X and Y are exactly the same text by text, it doesn't matter whether they contain variable, they contain constant, they contain whatever, the answer is always true. So I return a true, or I basically return the substitutions which are made so far. Absolutely okay. The next thing that could happen is that let's say that variables and the constants around over here. So if it's a constant, it will match as constant is equal to constant. Everything else will be failure. So everything else is failure, return. So if it doesn't match, x is equal to y, and some conditions that we'll write for constants, lists, and compounds. And of course, I need to recursively return it up. So if I get a failure, I return a failure. So let's handle the next best case, which is a variable. So either x can be a variable or y can be a variable. If x is a variable and if y is a variable, in both cases what I do is I give the duty to another function which I'll write separately, unify variable. So what's a variable? X is a variable. And if y is a variable, I return unify variable. So I'm yet to write this thing up. If something is, so y is the variable goes first. And then it could be a list or a compound. If list, then of course, in case of a list like AI, comma, best friend AI, so I reduce it as the first and the rest. I solve it for first and I recurse for rest. So that's recursively calculating the sum of a linked list. So what do I do is, if it's a list, then I first unify the first parameters. So the first item in X with the first item in Y, and I'll get some substitution, I'll get some theta that satisfies this. Of course, I have made some substitution, I'll have to pass that. The theta that I get as a result of it, that is what I pass to unify everything else. So then I unify rest of X, rest of Y with the substitution. So I'll very quickly go take a dummy example of a list X, Y, let's say 1, 2 as constant, Z as variable with, let us say, 8, 5 as constant, 1, 3, okay, I wanted to unify 1, P, and let us say Q. I want to unify it up, so I first take this out, which gives me a substitution X is equal to 8. Along with that, all the substitution that I would have been carrying in my theta. So I add the substitution in my theta, that's the result of this thing over here, the new substitution. And now my new theta, which is equal to old theta, along with the new substitution X is equal to 8, this is what I use to unify this thing. So unify all the rest, which is Y, phi, 1, 1, 2, P, Z, Q, and whatever I get, it's on the new theta, which is after unifying the first. So let's wait for compound. It's exactly the same. So if you look at it closely, this was the list and this was the compound. It was handled exactly like the list, where the name comes first and all the arguments come later. So I can just copy exactly the same thing. So return, what do? I first unify the name. So the name of the operation or the name of the compound with the name of the compound Y, and then the new theta that I get after this, that is what I add to my old theta. So comma theta. So I add this thing to my old theta. So this function unify will add whatever new substitutions have been made such that the names match. The theta, which is everything that has been substituted, along with the new substitution that are a return of this is what I'll do as the arguments of X and arguments of Y unify. So I just need to copy this up. So unify arguments of X and arguments of Y. And of course, finally I return a failure. And you should also be checking that Y is also a list. Otherwise, of course, it's a failure. Compound. So I get to the interesting part of it, which is to deal with how do I unify variables, and of course it's very simple. So unify variables. X is a variable and y could be anything, variable, no variable, and the substitution so far are theta. All that you do is just one line that you add x, y to theta and you return this up. Now, before you do that, there are a few checks that you might like to do. So let me just specify the exact inputs here. So this is a variable and this could be anything. The first check is that, let me see if I can quickly take in directly the examples. And I'll take in examples from maybe list itself. So the first list is x, y, x, 3, where numerals are the constants and otherwise. Now x is equal to 5 when you do the first, y is equal to 3 when you do the rest, x is equal to 8 when you do the rest, and there's a problem, x has two values. So you have to check that it doesn't already have a value. So if your variable already has an old value in your substitution so far, then I cannot call it as a failure, because if x was honestly 5, then it would have been a success. So I'd say the new value and the old value needs to be equal. The new value, so then unify under theta, the new value which is a y and the old value which is the old value, if both of them are equivalent, again whenever I need to say equivalent, I'll be very careful. I'll say unify. I cannot put a straight away equal to, because it needs to pass through a unification. Now that might not be the only problem. There is another problem. Of course, there's a occur check. So x cannot unify with best friend of x. So I just mentioned it as occur check. So if the occur check it returns true, then of course I return a failure, which is that x is not contained within what you want to justify it up. In the example, this is x and this is actually y. So the occur check must also hold good. Now there's another problem. So I'm trying to add x is equal to y in English language to my theta. I checked x does not occur in theta here. However, it may happen that y occurs in theta. Is that a problem? Maybe, maybe not. Let's mathematically look at it. I'll add x is equal to y and y is already in theta. That means there should be a y is equal to z in theta. That means y is equal to z is already there in theta. I need to x is equal to y. So I have x is equal to y, which I want to add. Y is equal to z is already there in theta. That basically implies y is equal to z should be compatible with each other. And let me write it down. So if instead y I just make sure y and z are equal, so I unify y and z. Okay, so let's take in a quick example maybe. So I say friends, and of course friends, and let's say that there is x I'll add later over here. So who's friends with x? So let's add best friend y. Okay, so let's very quickly do friends and friends will match. Y will get substituted by a best friend of x, and x gets substituted by y, which means x is equal to y is equal to best friend of x, which is basically indirectly, and that does not pass a check. So just check that y and z are compatible with each other, or x is a variable, y could be anything, another variable. So just check that if it has an old value, the old value and new value are compatible with each other. Similar to what we did it with x, you do it with y. And that's the only thing that we'll be doing. So whenever we need to say this is equivalent to this, we'll just call in a unification